And I'll switch to this conversation section. Recording has started. Good. Okay, so you see my screen, right?
Yes, sir.
Okay, good. Okay, so yesterday the attendance was even poorer, some around 10 to 12 students were there. But anyway, I considered that yesterday's session as kind of optional thing. If you have doubts, join. Anyway, we will see. So today we will solve a few problems on minimization of DFA, okay, and similar issues, which eventually culminates in a study of the Myhill-Neurath theorem. Okay. So I start with this standard old problem. Consider this language LK. L stands for last. Set of all strings over 0 and 1, binary strings, such that the kth last symbol of W is 1. So yesterday I actually proved that any DFA for LK contains at least 2 power k states. If you did not attend, of course, most of you did not attend yesterday's session. So you may look at the transcripts of yesterday's session and also the scribes. So you can find the proof. And then I mentioned that following a very similar idea, you can prove the result for NFA. So let me see if there is any progress about this. NFA, any NFA for LK must contain at least k plus 1 states. So any thought about this? No suggestions? Delta star actually hat Sx is in power set of Q, so to power this many choices. Yes, that's true. That's true. That's very much true. But then what after this? No, no suggestions are coming. And if it's k or less states, 2 power k is thus less than equal to 2 power k, 2 power q. Okay, that is true. So yeah, we have to work around that logic. So let me tell you. Suppose that some NFA n with less than equal to k states accepts Lk. Okay. So as in the proof I have given for part A, I considered the behavior of this machine n on this k input, all zeros, not all these k inputs, this 2 power k inputs. Okay. So all strings of all k length strings. And I apply this delta hat function starting from the start state. And so on. Delta hat of. Okay. So unlike in a DFA, these are actually subsets of Q. So Q is a set of states. So this is a subset of Q. This is a subset of Q. This is a subset of Q, and so on. By definition. Okay. So if this machine has less than equal to k states, then as is suggested in the chat section, we can have at most 2 power k subsets of Q. So this is one of these 2 power k subset. This is one of the 2 power k subset. This is one of the 2 power k subsets, and so on for every input, k length input. Okay. There are 2 power k of them, and there are 2 power k possibilities. So we still do not have more holes than pigeons. Okay. And we can still have all these states different. Okay. So I have still not reduced to a situation where I can use the pigeonhole principle. In order to do that, I first consider one case. Delta hat is on some string alpha of length k is the empty subset of Q. This is possible, right? In fact, if all these states are different, this case will happen when the number of states in the NFA is equal to k. Okay. So what does it mean? Delta hat S, starting from S, you read alpha, delta hat becomes the empty set. What does it mean? You tell what it means. No. Forget about the implications. What does it mean? Delta hat is alpha equal to empty. What does it mean? Then we will see its implications. Does not terminate. No, No, it's not the question. Terminated before the string end. It's not terminated, so this essentially means, yeah, machine gets stuck. At some point while reading this alpha. Okay, so this is the correct word. It gets stuck. It's not terminated. Okay. So it may happen at the beginning or after reading a few symbols or even after reading the entire alpha. Somewhere it gets stuck. Okay. Therefore, if alpha is followed by any beta, right, then the machine will also get stuck on alpha beta. No problem, right? Okay. So in particular, n also gets stuck on right? This will also get stuck on any string of the form alpha followed by 1 and any string you take of length k minus 1. Maybe it's 1 power k minus 1, 0 power k minus 1, anything. But this string should be accepted because the kth last symbol is 1. Okay. But the machine gets stuck. And therefore it rejects alpha 1 beta. Okay. That is not possible. So this leads to a contradiction. So this may not happen. Now, therefore, I may assume that none of these subsets of Q is empty. And now how many possibilities are there? It's no longer 2 power k because we have discarded this possibility. This is not possible. This is not possible because it leads to a contradiction. Right. So they are all non-empty. Now I can apply the pigeonhole principle. So I must have some input alpha I, alpha j, such that delta hat of S alpha I is equal to delta hat of S alpha j. Okay. So that means alpha I and alpha j are two different strings, but the delta hat value, which is a subset of Q, they are the same. And let us call it P. Okay. And since this alpha I and alpha j are two different strings, as I mentioned yesterday, they must differ at least at one position. So maybe this is 0, this is 1. Okay. And if this length is L, I append any string gamma whose length is k minus L. Okay. So if I append this with any string of length k minus L, this should be rejected because the kth last symbol is 0. This should be accepted because the kth last symbol is 1. Okay. But the acceptance or rejection of that string depends actually on delta hat. Actually, I'm using a bit of abuse of notation. I am using a subset here, P gamma. So it's a non-empty set. You apply gamma on it, and then you see whether this set, if you call it Q, I should not use R. Okay. If R contains a final state, okay, then it accepts both this and this. If R does not contain a final state, then it does not accept this or this, both. Okay. So in either case, we have a contradiction. Okay, so that ends the proof. This is essentially the same proof for DFA, where we considered only case 2. And instead of capital delta hat, we have used small delta hat. And otherwise, here this is a little bit complicated because of this extra case. Okay. So, yeah. Any questions on this? If not, we will move to a similar question. Is this fine?
Yes,
Yes,
sir.
sir.
Okay, good. Okay, so here what we have done, it's a very restrictive condition. One particular bit has to be 1. Okay, that is the kth last bit. So I relax this condition a little bit, and I want that among the last k positions, at least 1 should be there. Okay, so this leads us to this language. Here A stands for at least. So set of all binary strings such that the last k positions in W have at least 1 somewhere, not necessarily in the kth last position. Maybe in the last position, second last position, third last position, and there will be multiple ones, but at least one should be there. Okay. So question is, one thing is certain that if I remember the last k bits read, okay, then I can design a DFA using the same principles as exercise 1, right? So I can definitely remember last k symbols read. Okay, and this will lead to a DFA with how many states? 2 power k, right? And I am done if I can remember this k, last k symbols. Okay. So a DFA with 2 power k states accepts AK like LK. Okay. Now the question is, are so many states necessary? Because here the condition is somewhat more relaxed than the previous thing. Okay. You may have k positions in at least one position. You have 1 in at least one of the k positions. So can I manage with fewer states? Or in other words, so this is the precise question. Find the minimum number of states that a DFA requires in order to accept AK. K plus 1 states. Good suggestion. Why? Why do you think so?
Sir, like there will be k plus 1 state. So one state for accounting that there are no ones in the last k positions, and another for when a 1 appears in the last, uh, kth position from the last place, and then we can do it for all the k positions. Like,
Okay, whatever you told is not exactly clear, but its idea is fine. Okay. So let me solve this A first. So it suffices to remember when the last one is read. Okay, but of course, when I say when, this does not mean in among the last k positions. It does not mean before that. These things are not relevant. Okay, whatever you have read earlier, much earlier than these k states, for example, during Big Bang or during the Cretaceous period, whatever you read, that's not relevant. Okay. Of course, remembering all of the last k symbols will suffice, but it also suffices if we can remember the position of the last one read, but among these last k positions. Okay, so this will essentially give me k plus 1 states. The first one is all zeros. So no one is read among the last k positions. Or maybe let me, as a simplification, let me take k equal to 5. This will illustrate it better. Okay. So 5 zeros. I have not read. The machine does not have not read any one among the last five symbols. So this will not be an accept state, and this will also be a start state. And otherwise, it is also possible. Okay, so I will write star 1. Okay, so this star means, okay, so maybe I do not need to write the stars. Just write it as 1. Which means the last symbol read is 1. 1, 0, this means the second last symbol read is 1. After that, a 0 is read. And this initial part, remaining of the 5 bits or k bits, it's not important. Okay, so these are all accept states, final states. Okay. Now let us see the transitions. So this is not minus. Whatever is there, it doesn't matter. If a 0 comes, it will stay here. If a 1 comes, the last symbol read is 1. So this is 1. Likewise, everywhere, if a 0 comes, if a 1 comes, I will have a link like this, 1, 1, 1, 1. These are all ones because the last symbol read is 1. Okay. If a 0 comes, here I will stay in the same state. Here, 0, 0, 0, 0, And then if a 0 comes, I will come back here. So it is at least established that k plus 1, so in this case 1, 2, 3, 4, 5 plus 1, 6. So k plus 1 states suffice. Okay, but still we have not proved that. So I have already solved B actually, in a sense. Okay, because I have explicitly constructed a DFA for it. Of course, I have done it for k equal to 5, but this construction can be generalized to any value of k. Okay. So it is obvious that now it is obvious that k plus 1 states suffice. Okay. So you have to additionally argue that this is actually a minimal DFA, which means that you cannot reduce the number of states beyond k plus 1 to something smaller than k plus 1. Now, what kind of logic will you give for that? So would you like to use pigeonhole principle again? Maybe you can do it by using pigeonhole principle, but given a DFA, there is a better way of proceeding. We can get the equivalence relation of this DFA and prove that it is the same as the characteristic equivalence relation. You can do that, but that is a little bit more work than necessary. Yeah, you are on the right track, but it's a little bit complicated track. Use these relations, yes. So, yeah. So any other suggestions? Little bit easier suggestions? Prove that the courses partition has k plus 1 index. Okay, these are all essentially, yeah, this is also okay. Okay, this is also okay. But how about looking at this DFA itself? And if I can show that, first of all, how do I minimize a DFA? There are two ways, right? One, by throwing away all inaccessible states. But here you can see that all the states are accessible. Okay, starting from here, 1, 0, 0, 0, 0, these are all accessible states. Yes. So that's the suggestion. No two of these states can be collapsed. Okay, so how do I argue here? Of course, I cannot collapse these with any of these states because this is a non-final state. These are all final states. I can never collapse a final state with a non-final state. So only possibility is that whether I can collapse any of these 5 states, any 2 of these 5 states. Okay. Why is it not possible? Zero transitions lead to unique states. No, that doesn't matter. You are on the right track again, but this does not matter. Different states do not mean inequivalent, non-equivalent. Okay, we have seen examples where, yeah, from 2 states, 0 leads to 1 state, 1 leads to another state. So there are 4 states. Okay. So if you have a situation like this, 0, 1, 0, 1. Now, if it turns out that this is equivalent to this, and this is equivalent to this, okay, then they become equivalent. So uniqueness does not help. Right? So this and these are different states. But if they are equivalent, and if this and these are also equivalent, then I can make these two equivalent. And I can merge them, collapse them. Okay, so no, it's okay. Yes, I understood my mistake. It's okay, but again, I would say you are on the right track. None of them are equivalent. Yes. Why? That is the question. Why? So let us see why this and these are not equivalent. Yes. Yes. So this is the correct answer. Okay, so you read it. For any 2 states, we can find a 0 string of size, say k, not k, then let us not use this k, some L. Then we can show that one leads to final, another leads to non-final states. Yeah, that follows from the definition. For example, if I look at this state, and if I consider this string 0, 0, upon reading 0, 0, from this you are ending up in a final state. But if you start from here, then if you read 0, 0, you end up in a non-final state, this one. So this and this cannot be equivalent, right? And this example easily generalizes to a general proof, because the structure of this will be the same, irrespective of the value of k. Right. Okay, so given this, instead of don't write k, write L or something like that. So then they will make the perfect proof. Okay. So these states are all inequivalent, mutually non-equivalent. And they cannot be equivalent to this because this is a non-final state. Okay. Okay. So, yeah. So let's see. So we have actually solved B and A together. Okay, the earlier suggestions like computing the index of this language, these things will also work. Okay. but maybe a little bit more complicated. Anyway, any such proof will be based essentially upon this idea. Okay, it doesn't matter anyway. So let's see whether there is any question. Understood?
Yes, sir.
Okay, so why they are not equivalent? Any two of these are not equivalent. It's clear, right? Okay. So I give you a third language of a very similar flavor, but I will not solve it. I will leave it to you. Okay, but I just want to mention this. So this is another variant. So this A now stands for exactly one. So set of all binary strings such that the last k positions of W contain exactly 1, 1. Okay. It can be in any of these places, last one, second last one, third last one, fourth last one, up to kth last one, but it must be exactly 1, 1. Okay. And then repeat the same thing. Find the minimal number of states and design a corresponding DFA. Okay. So in essence, this is a little bit more restrictive than the previous example, right? Where you may have 1, 1 anywhere, but at least 1, 1. But here I am demanding exactly 1, 1. Okay. So with this added restriction, does it mean that you still require 2 power k states? Maybe only this part. Let us try to solve. The rest I will leave to you. So once again, the idea is similar. If I can remember the last k symbol straight from the input, then definitely I am done. But is that necessary? Without knowing the exact position of the ones in the last k position, we can never tell that after appending 0 or 1 to the end, how many ones will be there in the last k position. So your suggestion is that 2 power k states are necessary. Yes. Okay. Let us see if there are any more suggestions. Okay, so what I want to, so let's take small value of k equal to 1. Definitely this strategy will require two states. 2 power 1 is 2. But a one state DFA cannot accept this string, this language. A one state DFA can accept either the empty language or the entire sigma star, right? So this is true. For k equal to 2, what should be the 2 power k based approach? Let's see. This is read 0, stay here. If you read 1, you come here. If you read 0, you go here. If you read 1, you come here. If you read 1, you come here. If you read 0, you come here. Here, if you read 0, you come here. If you read 1, you go here. So this is a DFA that I can construct using the strategy of remembering all of these last k steps. So can you collapse this machine? Yeah, tell. Is it a minimal DFA? Yes or no?
Yes, sir.
Right. Why? Because I cannot collapse this with this, or this with this, or this with this. Only possibility is I can collapse this or this. But this and this are not equivalent because upon reading 0, this goes to a final state. Whereas from here, if I read 0, I go to a non-final state. So they are not equivalent. Are they equivalent? Again, you see no. Upon reading 1, this is accept. But upon reading 1, this is reject. So this is once again minimal. So the number of states is once again 4 to power. Okay. There is another suggestion. Let me see. We can store the digit at the kth position and the number of ones. Then after letting a 1 or 0, we can determine which state we will end up in. What is your suggestion? Final conclusion.
First, sir, we'll require two case states. Like the
Oh, so your suggestion is that this is a proof of the fact that this is true.
like two, like not 2 to the power k. We can work with two case states also.
Okay. None of the final states can be collapsed, nor non-final states can be collapsed for any k. For any k. Now, what are you answering, Saumita? Are you proving or disproving or what?
We can always find zero string of some length so that we end up in a final state for one case and in a non-final state for another case.
No. So, what is your conclusion? 2 power k states are necessary.
Yes, sir.
Let us take k equal to 3. Consider these two states. Zero, 1, 1, 1, 1, 1. So if I read 0 from here, where do I go? 1, 1, 0, right?
Yes, sir.
If I did 1, I will go to 1, 1, 1. If I did 0, I will go to 1, 1, 0. If I did 1, I will go to 1, 1, 1. They are both non-final because the number of ones is larger than 1. And this state is same as this state, and this state is same as this state. So this state there must be equivalent. Yes or no? Yes or no? You tell. Okay. So 2 power k states are not necessary. You can see this is equivalent. Now this is the same state, and same state means they have to be equivalent. 1, 1, 1, 1, 1, 1. Okay. So 2 power k states are not necessary for k greater than 3, for k equal to 3. Okay. So I will not proceed further. I leave it to you as a puzzle to find out as a function of k what is the minimum number of states needed. Okay. If you want, I can also tell you the solution. You try to prove it. Shall I tell you the solution? The final expression of the minimum number of states as a function of k. What do you think? Or you will figure it out? Tell something.
Sir, some hint probably.
Okay, I will tell you the answer. Hint you find out. From the answer whether you can. These many states are needed. K plus 1 choose 2 plus 1. Why? Okay, maybe you think. So this is an interesting puzzle. You think. Okay. On a later, during a later meeting, maybe we will discuss this. Meanwhile, you try to think why these many states are necessary and sufficient. Okay. So let us move to another question. Oops, we are already 12:03. Okay, so this is another important thing. So far, we have been talking about minimal DFS, but we have not made. Yes, there is somebody wants to say something.
Yes. So I was saying that we look for the larger values of k only in these cases, because for some small k, it might happen that some worse function is greater.
Take
Sorry,
k equal,
smaller.
no, this one. Take k equal to 1. What is this expression? If take k equal to 1. So 1 plus 1, 2 choose 2 is what? 1 plus 1. 1 plus 1 is 2. Okay. So it happens to be same as 2 power k. If I take k equal to 2, 2 plus 1 choose 2. That is 3 choose 2 is 3. 3 plus 1 is 4. So that is once again equal to 2 power 2. So this formula is valid for k equal to 1 and 2 also.
So, but it might happen that for some function, means it is asymptotically smaller, but at some smaller values, it might be greater. So means that doesn't matter. That only I was asking.
No, I didn't understand your query. This is the exact.
Suppose it is 2k plus 1.
2k plus 1.
I mean, suppose some function comes 2k plus 1, but
Uh-huh.
2 power k is smaller at k equal to 2.
No, I'm really confused about your query.
So I just want to know that is it supposed to be true for all values of k or for larger values of k?
For all values of k. Yeah, this is true for all values of k. As in the previous one, it is k plus 1, right? So the answer is k plus 1, and that is irrespective of any value of k. K equal to 1, 2, 3, 4, 5, everything is fine. Here also this formula is valid for any k, of course greater than equal to 1. K equal to 0 makes no sense. Okay. Okay. Yeah, prove that the minimal. Okay, so we have never made an attempt to minimize NFA. There is a theory on it, theory of bisimulation and all that stuff. Let us, well, we prefer to skip those things. It is only, I would say, instructive to note that the minimal NFA for a regular language need not be unique. That is, you propose two different, structurally different NFA with the same number of states, should be minimal to accept the same language. Good. Good. Yeah. Yes. This is a good idea, but I will take even a simpler thing. Because how many states? You require 3 states for realizing either of these, right? And then why 3 states are needed? Why can't you do it with 2 states, 1 state? These things you will need to show. Okay. Instead take this, L equal to A plus. So I can write it, this is same as A star A. So if I look at it in this fashion, then I have a thing like this. First read A and then loop on A. And here, first loop on A, then read A and accept. So they are structurally different, right? But they both accept the same language. It's language of A plus. And of course, in order to complete the proof, you must show that no one state NFA can accept L. Okay. And this idea is also very similar, 1 0 whole star 1 1 followed by 0 1 star. Okay, but actually you have to show that why 2 states cannot suffice. Okay. Yeah. Okay, so what is the time? 12:15. Maybe let us have one more. This is actually an explicit example. I suggest that you work it out. Let me give you something a little bit more conceptual. This one maybe, which is an application of the Myhill-Nerod theorem. Okay. So consider this. We have proved in 2 different ways that this language is not regular. Okay. The number of all strings over A, comma B, such that the number of A's is equal to the number of B's in that string, in those strings. Okay. So, of course, we have seen a proof based upon bumping lemma. We have seen a proof based upon, let's say, closure properties, given a proof of non-regularity of A power n, B power n. Now, if I ask you to use Myhill-Nerod theorem, let us see an application of Myhill-Nerod theorem. Okay. So what do you have to do? If you have to use Myhill-Nerod theorem, what do you have to do? Yes. Good suggestion. So infinite, the equivalence class corresponding to this language does not have finite index. So this is a better statement. Index of equivalence relation is not finite, but what equivalence relation? It is this relation. So to show that the equivalence relation corresponding to this language EQ has infinite index. Okay. Good. So that is the way we should proceed. But how do or what do the equivalence classes look like? Okay, so in other words, what are the equivalence classes? And once we understand what these equivalence classes look like, we can say there are infinitely many of them. So what are the equivalence classes? Based on the number of A in W. No. You're again on the right track, but this is not the correct answer. A power n hash AW, no. No. Oh. Okay. No, okay. Based on the number of A's in W. This is not correct. This does not, this is not a clear statement because hash A of W, what is W? And this is an integer, this is not a string. Write it clearly. So we are talking about equivalence classes of strings, right? Not of integers. Equivalence class of A power n. This is actually correct. No. No, this is also not fully correct. No, this is also not fully correct. No, this is not correct, but this is the best suggestion so far. Okay, so equivalence classes are essentially based upon okay, hash A in W minus hash B in W. Okay, so let's say how do I write? The equivalence class of some string W consists of all X in AB star such that number of A in X minus number of B in X is equal to number of A's in W minus number of B's in W. Or maybe I write it a little bit. This way, where this A stands for surplus of A's over B's. Okay, so why? Okay, so this is the surplus function. Number of A's read in X minus number of B's. Surplus of A's over B's. This may be a positive value, negative value, 0. Okay. But why is the equivalence class like this?
Sir, are you asking like to prove that this is an MN prime relation? That thing are you asking?
No. First of all, how do you define this equivalence relation? Recall that. Okay. So you are given some language L, not necessarily regular. You define this X is a string. What is the definition? If and only if
XZ star y is equivalent to YZ star for any Z belonging to sigma star.
X for any Z, for all Z, you have this. Okay. If and only if, so this is the definition. So all definitions are if and only if for all Z in sigma star. What do you have? XZ is in L if and only if YZ is in L. Okay. So this is not my Hillier or whatever, it doesn't matter, Mn or Mn prime. This is how this is defined. Right?
Yes, sir.
Okay. So now if you consider this, just write L equal to EQ. Then you prove this. Okay. If X and Y have same surpluses of A's, then whatever string you append, this condition holds.
Yes, sir. So like if like Z will have to have a minus S of X, which is the same as minus S of Y.
Yeah. So it's fairly straightforward. If you just follow this definition, this is fairly straightforward because the surplus of XZ is surplus of X plus surplus of Z. Surplus of A in Z. Okay, surplus of A in XZ is this. And YZ okay. Now if X is equivalent to Y, so Sx is Sy if and only if for all Z Sxz equal to Syz. Right. Okay. So now if this value is 0, then both Xz and Yz are in L. If this value is non-zero, neither of them is in L. So this condition holds. Right. So based upon these surplus values, you can define equivalence classes. And what is the surplus value? This is basically an integer valued thing. 0, 1, -1, 2, -2, 3, -2. So there are infinitely many equivalence classes. And therefore, this cannot be regular. Okay. So maybe I just end this today's tutorial by doing the same thing. Consider this language and find all the equivalence classes of this. Same relation, but this time this will be finite because this is a regular language. A star B star plus B star A star. So what are the equivalence classes? With respect to this definition. Okay. Not with respect to, no machine is involved in this context. So given the language, you are defining the equivalence.
Sir, could you also please solve the last problem from last tutorial, like last Friday's tutorial?
What was
The one,
that?
like there exists a language in 0, 1 star such that no infinite subset of L or L complement is regular. So prove that this exists.
I now remember. Do you want me to solve? I can solve. Why don't you think?
I don't know. So I got stuck. Like I was trying ultimate periodicity, then trying
Okay,
to
fine.
show the diagonalize the thing, but it didn't work out.
No, it's okay. It's okay. Let us first concentrate on this exercise, then I will tell you or give you an explicit hint. Okay.
Yes, sir.
What
Hint will be better.
Yeah. Good. Epsilon, A plus, B plus, A plus B plus, B plus A plus. Good. Okay, so or let me simply write this. A plus consisting of all strings, B plus, I should write language of this, but anyway, abuse of notation. I'm using this symbol. Actually, there is one thing missing. So one equivalence class is missing. All strings containing both AB and BA. Okay. So you have to give a partition of this entire sigma star. So why? Okay, it's not very difficult to figure out why. First of all, this is not in the language R. Okay. This is inside R, this is inside R, this is inside R, and so on. Okay. So there is no question of having this or this equivalent. Okay. Definitely no member of this or this can be equivalent, because in that definition, this definition, if you take z equal to epsilon, right, you can take z equal to epsilon in this. Okay. And this is not in L, any string here, not in L, whereas any string here or here or here, they are in L. So they cannot be equivalent. Okay. So, however, so you have to prove that how many classes? 1, 2, 3, 4, 5 classes. Okay. You have to show that they are pairwise disjoint. Okay. So no string of the form B plus can be equivalent, for example, to a string of the form A plus B plus. Why? So this is example. No string in B plus can be equivalent to any string in, let's say, A plus B plus. Why? Yeah, take Z equal to A plus. Good. Z equal to A. Why A plus? Just A take. Then a string, take any string of the form B plus, append A. It will continue to be in the language, but if you append A here, this will not be in the language. So they cannot be equivalent. So this way you can actually find out this is not equivalent to this is not equivalent to this is not equivalent. These are all pairwise different. Okay, non-equivalent. Okay, so that's it. In fact, this also follows from this DFA. Sorry. right? So this corresponds to this, corresponds to this corresponds to this state corresponds to this state corresponds to this to this, and the remaining things this. Okay. So this has natural one-to-one correspondence with this minimal DFA. Okay, fine. This is another way of looking at it. Okay, so I could not complete just one, so it would be good that you try this. Draw the DFA and run the DFA minimization algorithm on this small example. 5 states. Okay. And if you want, I can solve it here. I mean offline and post it. What do you think? Shall I solve or you do it yourself? Of course, there are other examples. This is just an explicit example. You just draw the DFA and run that minimization algorithm. Okay. So I'm not doing it now because it's already 12:40. Now there is a request to solve, or at least give some hint for what is that? Example of L in AB star such that neither L nor its complement contains an infinite regular language. Okay, so we have seen that if L is regular, then or maybe I use some A because L has some other meaning. The set of lengths of strings in A is ultimately periodic. Okay. So if you can build L and not L consisting of strings such that there are arbitrarily large gaps in the lengths. So some lengths may be like this. So this is in L, this is in L, this is in L, not L, the remaining things. Okay. And so just work out how you can gradually, you would say, widen this gap. Okay. So it's simple actually. Take 2 power n plus 1. This kind of thing. Maybe you include this, exclude this. And alternately take this here, this here, this here, this here, this here, this here. Okay. So this means this is a gap. This is a gap. This is a gap, and that gap will keep on increasing. Here also in not L, this is a gap. This is a gap. Okay, so the gap will keep on increasing. So if there is an infinite subset of L or not L, complement of L, then its length will have to be ultimately periodic. But if the periodicity is something like P, at one point of time, this gap length will exceed P. Okay. So that's the basic idea. So is the hint okay? It's more or less explicit.
Yes, sir.
Is this fine? Okay. So this is one way of constructing such an example. Yeah. So I think we stop here. Anyway, we have solved quite a few exercises, but you didn't tell. Shall I solve it before posting? This is just a numeric exercise.
So maybe afterwards we can check. So not now.
Yeah, it's very, very simple thing. Yeah, we will just check the solution. I have not worked it out yet because it's just a 5-step DFA minimization. Okay, so you work it out as a practice. And this, of course, I remain open for the moment. Okay, so let us stop here. Oh, next week we had some test, right?
Yes.
That schedule was there. So yeah, so be prepared. It's a long test, so maybe around 11 to 11:50. Okay, so let us do it in Moodle itself. So you try to try so that you just know how to prepare a single file for all solutions, a single PDF or single zip. Okay. So we will give you certain time, something like 5 to 10 minutes for doing this. Okay. So maybe it's a 50-minute test and 10 minutes for submission. Can we please keep it like last time? What is last time?
So like submitting the PDF in the Google form, because similar problems with Moodle occurred in software test also. When like many people are trying to submit at once, it crashes. That's why. That's why, sir.
No. So you suggest Google Form. Okay, we will follow Google Form. So instead of
Yes,
Moodle, you are asking Google Form. Okay, we will
yes,
take
sir.
Google. Okay,
Like,
no
like,
problem. Okay, we will use Google Form. And we will, okay, but try to answer everything. I mean, the upload mechanism will be a single file. Okay, that is fine, right?
Yes, sir.
Yes, sir.
yes, sir.
Okay, so try to give a single PDF. If you cannot generate a single PDF, just give a zip file of individual pictures, individual screenshots or whatever. Okay, so we will use Google Form, no problem. And that includes everything about regular languages. That is the syllabus, because we have covered all the relevant parts in tutorial sessions.
So we'll have a doubt clearing session on Thursday, and after the exam from 12 to 1, we'll have a tutorial as well.
Yeah. So from next week, we are starting context-free languages. Yeah,
Yes.
so I upload the links today or tomorrow, video links. Okay, so any other question?
Sir, for long test, the syllabus will be till this point, right?
Till this point, yeah.
Yes. Okay.
Okay.
Sir,
Yeah, any other question?
sir, for that submission part, keep it on CC model because it's better than the Google Form. Since Google Form takes only single submission, in the Moodle we can update things. Means CSV model is far more reliable.
No. What is your suggestion?
For the long test submission, keep it on CSV model.
Submission on CSE module.
Okay,
No,
it's last semester it proved reliable.
no. You decide. I also wanted to make it in Moodle, but because most students told that Google Form will be better, and I hope it is slightly better. Okay.
But that is, I think, single submission. Only once you can make at the end. Okay, sir.
No. If you together decide that Moodle will be better than Google Form, and I can go ahead. Either way, it's okay with me. But I have the impression that most of you are actually preferring Google Form.
Okay, sir.
Okay.
So the thing is like I don't like there's no problem with CSE Moodle, but like people tend to upload at the last moment. So if like 50 people upload at once, Moodle tends to crash at times. So that's the only reason.
Yeah, in that respect, Google Form is a little bit, I would say, more stable. Even if 1,000 students try to access at the same time, it will not crash or hang. Yeah, that's the only difference. Yeah, that's I understand.
Sir, but like if we use CSE Moodle, then like even if you upload 1-2 minutes late, it will get stored in CSE Moodle. Like, but if we on Google Form, it gets the form closes at the given time.
Well, that depends upon your Moodle settings. If you give some grace time, then it will remain open. And Google Form, what will happen? I actively didn't try. But anyway, if necessary, we can give you a couple of minutes extra. So let us go ahead with Google Form then. Maybe that is that will be more hassle-free for both you and us. And in the end, if you need some 2 minutes extension for submission, we will anyway give it to you. Okay.
Yes, sir.
Okay. Then Google Form. Okay. Okay, but there will not be individual solution links. You will upload only one file. This is fine, right?
Yes, sir.
Yes, sir.
Okay, great. Okay, then see you on next Thursday. Have a nice weekend. Bye.